Now let's talk about one of those approaches for selecting the optimal values for those hyperparameters, right? So in the previous example, we looked at how to do this ridge regression, right? But in order to do this ridge regression, we have to introduce some hyperparameter, that's lambda, and you have to choose this lambda intelligently, right? In order to actually get a compromise which actually fits both the data and also minimizes the L2 norm of the parameter theta, right? And another hyperparameter that we have to sort of consider is actually the width of the Gaussian kernel function h, right? We have to sort of intelligently select h so that the fit to the data is not we come up with a compromise between the fit to the training data and also the smoothness of the function, right? So we have two hyperparameters, both h and lambda here, right? So is there any systematic way for us to choose those parameters automatically, right? So we don't have to sort of try many different values manually and then see which one actually gives us a good compromise, right? Yeah, let's talk about one of those approaches, which is called cross-validation. So before we actually do anything, let's create those fake training data, right? So import numpy as np and then import matplotlib.pyplot as plot, right? Then let's generate fake training data, right? Again, we're going to use n equals to 50 points, and x is going to equal to np dot linspace minus 3 to 3, and then n, this many points, right? And then pix is going to equal to np dot pi times x, and then our fake label is going to equal to np dot sign pix divided pix plus 0.1 times x plus, and this time we're going to increase the amplitude of the random noise from 0.05 to 0.2 just to test out how just to make it more obvious about how the cross validation can help us to choose the most appropriate parameters or most appropriate hyperparameters in an environment with very large random noise, right? And np dot random dot rand n, right? So now if we actually make a plot xfbo, then we should be able to actually see the noise to be quite big. Oh, okay, let me choose. So this is gonna be E11, right? So yeah, the random noise is kind of big, right? It's quite big. It's quite big. Certainly much bigger than the two previous examples, right? So okay, so now let's try to write the code for selecting the most appropriate hyperparameters that we're going to use, right? Let's call it cross-validation. Cross-validation in the training. Cross-validation. Let's just get rid of them. So the basic idea about the cross-validation is that we separate our training data into, so here we have like a 15 training data, right? So we can actually separate those training data, 50 training data, into multiple groups. So suppose we separate it into like 5 groups, right? Suppose we separate into like multiple groups, 5 groups, right? We separate them into 5 random groups, right? It doesn't have to be. We don't want to separate them into groups with duplication. We don't want to duplicate them. We want to separate them into 5 independent groups, and each group has different elements, different training data sets, right? And then we're going to train our model based upon 4 of those 5 groups. We're going to leave out one of those groups, right? So if we're separating the 50 training data into 5 groups, then each group is going to have like 10 training data, right? So we're going to train our model based upon 40 of those training data and leave out 10 of those training data as some kind of validation, right? So we're going to train our model. So the theta hat is going to be computed based upon only 40 of those 50 training data. And then the theta hat, the optimal theta hat, is going to be used for making predictions at those 10 training data that was left out during the training process, right? And then we're going to find out how good the fit actually is for those 10 training data that was left out, right? So if we are overfitting, so suppose we are overfitting, if we are overfitting the 40 training data, right, used for computing theta hat, then the theta hat obtained from this kind of overfitted process is going to have a poor prediction about the 10 training data that was left out, right? So this kind of thing actually prevents the process of the possibility of overfitting, right? If you fit the 40 training data too good, in the sense that you are fitting the noise in those 40 training data, right? Then the theta hat is not going to be optimal for the 10 training data that was left out, right? Because the theta hat was trained to fit those random noise in the 40 training data, and those random noise are not the same for the 10 training data that was left out of the training process. So that was the basic idea. So we try different values of lambda and different values of the width h, right? And see which lambda and h values actually gives us this kind of a combined effect of fitting the data, and then without actually compromising the fit to the validation data, right? So the explanation is kind of complicated, but the code is not as complicated as you might think. So we have to actually come up with some possible choices for h and also for lambda, right? So HHS is going to equal to 2 times mp dot array 0.03, 0.3, and 3, and then square, right? So we're going to try 3 different values for the width of the Gaussian, the kernel function, 0.03, 0.3, and 3, right? We're going to try these 3 different values for h. And because we're actually using h squared and then multiply 2, so we're going to sort of do a component-wise square for the elements in the array and then multiply 2. So we don't have to actually compute the square and the multiplication repeatedly in our loops, right? So that's 3 values that we're going to try out for different values of h, right? And then we also need to try out different values for lambda, right? So let's come up with another array. Let's call it AMS lambdas, right? It's going to be amp.array, and we're going to still try 3 different values for lambda. So 0.0001, and then 0.1, and then 100, right? Let's try different values for lambda also, right? We're going to try 3 different values for h, 3 different values for lambda, and see which combination of those h and lambda actually gives us the best fit to the validation data, right? And another thing that we need to sort of, in order to actually reduce the kind of a repetition of the the same calculations in the loops. One of the things that we may want to compute outside of the loop is this array, right? So this minus x subtract xj square, this part of the calculation is independent of the values of h and also independent of the values of lambda, right? So at least we can actually compute this x subtract xj square with a minus sign outside of the loop, right? So that's something that we can prepare before the loop to reduce the kind of repetition. So b equals to n, that's the number of bases, right? And then kx, we're going to call this particular component the kx, right? Kx is going to equal to np dot zeros n and b, n rows and b columns, right? And then for ii in range of b, the kx, the ii's column is going to equal to minus x subtract x ii square, right? Maybe get rid of the space here. Right. So later on, once we have to actually compute the kernel function, all we have to do is to take the exponential of kx now, right? Take the exponential of kx divided by one of those elements in the HHS, right? One of those elements in the HHS is going to be 2 times h squared, right? And this way we can actually reduce redundant calculations, right? So now let's come to the code for doing this cross-validation thing. So we have to actually separate our training data into 5 different groups randomly, right? So how we are going to do that, right? How we are going to do that? So one of the functions that might be useful is called permutation. So amp.random, this particular library, actually has a function called permutation, right? And this function is going to take an input. Suppose that we give it an input like 5, right? So it's going to generate an array, but the elements inside of it is going to be a random permutation of 0 to 5, or 0 to 4, right? So 0, 1, 2, 3, 4. So every time you call this function, it's going to generate a random permutation of the same set of indices, right? So now if we actually do this thing into 50, then it's going to generate a random permutation from 0 to 49, right? So this way we can actually create a random permutation of the indices of our training data. We have 50 training data here, right? So if we do np.random permutation and give it n, then it's going to create a random permutation of our indices for the training data, right? But that's not the goal, right? That's not the goal. Our goal is to actually separate our training data into 5 groups randomly, right? So how do we actually separate the data into 5 groups? We're going to use a function called modulus, amp.mod, right? And then we're going to use m as our as the second parameter of the modulation. So here, if I actually copy this code over, m is not defined. So 50, right? 5. So this way, I create an array that's also 50 elements, right? 50 elements. The length is also 50, right? But the elements inside of it is gonna be 0 to 4, right? It's gonna be the remainder. It's gonna it's if I divide all those random permutations by 5 and then take the remainder of that division, of that integer division, then the remainder is gonna be a number from 0 to 4, right? And because this permutation is random, so the 0 and 4, those remainders are going to be random permutations or random repetitions of 0 to 4, right? And this way, I can actually, if I index into the training data using those numbers, then I should be able to actually come up with 5 randomly generated groups, right? Separate groups. So that's exactly what I'm trying to do here. Right? So I'm gonna assign this array into U, into another array that's called U, right? And later on, I'm gonna use this U to create the random permutations. And now let's try to compute the loop, right? To construct the loop. So we're gonna have to loop through all the different widths of the Gaussians. So for HH in HHS, right? And then for LM lambda in LMS, right? So I need this kind of two nested loop, right? One of the things I can, once I fix the HH, once I fix the width, I can actually compute my kernel functions, right? So my kernel functions, let's call it phi. The design matrix is going to equal to np.exp. So kx is a numerator already, right? So all I have to do is to kx divided by hh, right? So that's going to be my design matrix for every choice of hh, for every choice of the h inside of this array of all possible widths, right? Okay. So I got my design matrix now, and this design matrix is going to be 50 rows and 50 columns, right? Because we have 50 training data, and then the number of bases is the same as the number of training data, right? So the column number is also 50, right? So now we have to actually select our, we have to randomly split our training data into 5 groups, and then pick one of those groups as validation data, right? So how are we gonna do that, right? So I need another loop, right? And inside of this loop, this II loop, let's call it a permutation loop, right? Or sort of a cross-validation loop, right? Inside of this this loop, I'm gonna separate my training data into 2 groups. What does it mean by separating it into 2 groups, right? First of all, I need to separate my design matrix into 2 groups, right? And then I need to separate the label F into 2 groups also, right? And how do I actually do that, right? So the groups that we're going to use for training is going to be called phi I. It's going to be the row with U not equal to I, and then all the columns. And then the corresponding label is going to be the F U not equal to I, right? Not equal to II, not I. Sorry. Right. So for the first iteration, II equal to 0, right? So I'm gonna look at the U matrix, the U array, and see which U index is not equal to 0. That's gonna give me 1, 2, 3, and 4, right? So as long as U is not equal to 0, then it's gonna be selected, right? So how many elements are going to be selected, right? Because this random permutation and then this modulation of 5 is going to separate the 50 elements into 10 elements, 10 into 5 groups with equal number of training data. So U not equal to 0 is going to give me exactly 40 rows, right? The column number is still fixed at 50, right? Why is that? Right? Because the column number is actually the basis number. We are not changing the basis. We are only changing the training data. Right? And the same is true for the label, the manual selected label for the training data. Right? And then the validation group, let's call it control group. Phi C is going to equal to phi, and we're going to flip the condition. So here it's not equal to, right? I'm going to change it to equal to. And then FC is going to equal to FU equal to II. Right? That's the flip of the condition. So that's going to be our validation data set. Right? So we're going to train our model. We're going to compute theta hat using these 40 data, 40 training data. And then we're going to try out, or we're going to test how good that theta hat is on this control data. And this control data, or the validation data, cannot be used for computing the optimal theta hat. Do you see the idea here? Do you see the idea here? So theta hat, once we have the phi hat, phi I and fi, theta hat can be computed, right? Theta hat is going to equal to, we're going to use our equation here. That's this equation, right? Considering W as a identical matrix, right? So that's going to be NP dot link L P inverse. So here, because phi is no longer, phi I is not a symmetric matrix anymore, so we have to do this transpose now, right? So phi I dot transpose, right? Phi I dot transpose, and then dot. We're doing matrix multiplication, right? Phi I, right? That's gonna be this particular term, right? And then we have to add. Okay. We have to. Let me split it into multiple lines. Line continuation. Let me do line continuation here. Right, line continuation, and then this has to add LAM lambda times NP dot EYE n. Right. Is that right? Lambda times the identity matrix. So phi transpose. So phi I is gonna have how many? 40 rows, 50 columns, right? If I transpose it, it's gonna be a 50 row, 40 columns. So it's 50 by 40. And then 50 by 40 times another matrix phi. That's 40 by 50, right? It's gonna give me a matrix 50 by 50. Right? 50 by 50. So add another matrix. This identity matrix, that's also 50 by 50 because n is 50, right? So that's gonna give me the inverse here. That's so PIMV is gonna give me the generalized inverse here, right? And then this thing has to dot with what? Dot with phi transpose times F, right? Phi transpose, that's phi I transpose, right? Phi I transpose, and then dot Fi. Right, so to make sure that the parentheses are balanced, right? Yeah, that's it, right? So that's gonna be my optimal theta that's trained using only 40 of those 50 data, 50 training points, right? And then I have to use this. This theta hat to make some predictions about the label for the 10 data that was left out, right? 10 training data that was left out. How do I actually make this prediction, right? It's actually quite easy. All I have to do is to actually use phi c to dot theta hat, right? If I do phi c dot theta hat, then I'm actually making a prediction. Phi c dot theta hat. So again, the transpose is unnecessary if I do phi c dot theta hat, if I switch the order of it, right? So phi c was actually the phi, the design matrix for the 10 training data that was left out of the training process, right? And then all I have to do is to actually multiply it, do a matrix vector multiplication with the theta hat that was trained using those 40 training data, right? And that's gonna give me an F, or prediction of the F, for the control data, right? But don't forget, this prediction is not going to be identical to this FC, right? The actual manual pick, the actual manual label, right? It's not going to be the same. It's not going to, because the actual label actually has random noise in it, right? So let's subtract them. That's going to give us a residual, right? And how good our prediction actually is for the validation data is going to be measured by this residual, right? But this residual could be positive and could be negative, and it's going to be a vector, right? Because it's going to be a vector of 10 elements, right? So what we want to do is to actually square it. We want to square those residuals, which could be positive and negative, right? And then take the mean. We're going to take the average of it, right? And that's going to be our estimate of the error for the validation data, and we want to store it. We want to store it inside of this. We want to store it somewhere. So let's call it d mean. It's going to equal to zeros, mp dot zeros, m rows 1 column, right? And then d mean the IIS element is going to equal to this particular mean, right? So II is going to go through 5 iterations, right? 5 iterations from 0 to 5, right? So d mean is going to have like 5 elements inside of it, right? And this d mean array is going to be different for different choices of lambda and the HH, right? The lambda and the width of the Gaussian, right? So for a given choice of lambda and HH, what's going to be the average? What's going to be the average of d mean, right? Let's store that. Let's also store that, right? We're going to store that in another array. Let's just use a numpy list to store that, right? So ds is going to equal to mp dot mean of d mean, right? So every time we try a different combination of HH and lambda, we're going to store the average of the d mean here, right? So every element inside of this d mean vector is going to correspond to one choice of the validation data set, right? And this validation data set actually is only like 10 elements, is only the 10 training data that was left out of the training process when computing theta hat, right? So now we can actually close our loop now. We can close our loop now, right? So ds is going to have how many elements? It's going to have so we have 3 elements in the HHS array. That's 3, right? And then we have 3 elements in the lambda s array, right? So 3 by 3, that's 9. So the ds list is going to have 9 elements in it, right? And we want to actually reshape these 9 elements 1-dimensional array into a 3 by 3 2-dimensional array, so we can actually look at the values. Look at the values for different choices or different combinations of h and lambda, right? So we're gonna do this thing. dd is gonna equal to. So ds is a numpy array, right? It's not really. ds is in a Python list. It's not a numpy array. So let's convert it into a numpy array, right? And then we're gonna reshape it. Reshape it into what kind of shape? mp.size. The outer loop is HHS, right? And then the inner loop is going to be LAMS, right? And that's going to give us the correct shape and it's going to be a NumPy array, right? And we may want to look at the index. We may want to look at the index, right? We may want to look at the index. So how do we actually look at the index of this DD matrix, right? So how do we actually get the index that corresponds to the minimum value of the DD matrix, right? We have used argmax before, right? So argmin is going to give us the index corresponds to the minimum value of this DD matrix, right? But the problem is that this argmin doesn't have to be a function call. So you have two different ways of doing this thing, right? One is to do a function call, right? And another way is to actually to use it as a member function, right? But the problem with this argmin call is that it's not going to give us a two-dimensional index. It's going to give us a one-dimensional index. And this one-dimensional index is not really. It's kind of it's difficult to understand this one-dimensional index and how do we actually convert it into a two-dimensional index, right? But the good thing is that NumPy actually provides us with a function which is called unravel index, right? This unravel index is going to convert that one-dimensional index into a two-dimensional index for us. But the second input for this unravel index function call is actually the shape of this two-dimensional matrix, right? And then we can print it, right? And that's going to tell us the row and the column index corresponds to the minimum value of the DD of this two-dimensional DD array, right? If we run it, it's going to print out this index as a tuple, right? 1 1 1 1. 1 1 means what? 1 1 means so Python is zero-based indexing, right? So 1 actually means the second element inside of the. So it's actually the second row and the second column of your matrix, right? Of the DD matrix. The second row, second column actually corresponds to what? The second row actually corresponds to the second element inside of this HHS array, which is going to be 0.3, right? And then the second column is going to correspond to the second element inside of this inner loop, which is actually 0.1 for lambda, right? So the minimum value for DD, which is actually a average of the cross validation based upon the for the validation data set, right? The error on the validation data set, the average error on the validation data set, right? Actually, the minimum value of the average error on the validation data set is at width equals to 0.3 and lambda equals to 0.1, right? So this is actually telling us that. But let's try to create some figures, right? Let's pot.plot. We're gonna use the lambda as our horizontal axis, but because lambda has such a very wide range, we're gonna take the the 10-based log on it. We're gonna mp.log 10. Without the 10, that's natural log, but with 10, it's 10-based log, right? LMS, that's gonna be our horizontal axis, and then the vertical axis is gonna be DD. We're gonna start with the zeroth row. The zeroth row is gonna be correspond to HH equals to what? 0.03, right? And then we're gonna use red circles and with a line, right? And then pot.plot mp.log 10 LAMS DD, the second row, right? And then we're gonna use blue cross with a line connected them, and then pot.plot mp.log 10. It's gonna be DD2, right? And then this time we're gonna use black triangles with line connecting them, and then we're gonna add a legend, right? And the legend is going to be a list of strings, h equals to 0.0, 0.03, right? 0.03, and then h equals to 0.3, and then h equals to 3, right? And that's going to be our plot for the 3 different choices of h, and then 3 different choices of lambda, right? So let's just plot it. Oh, sorry, I'm not supposed to actually plot them on top of the training data. Let's just do another. Let's just comment out this training data because it's not really useful. We don't really need to plot this one. Oh, right. And then now let's run it. And that's going to give us some indication about what's going to be the optimal value, right? The optimal value corresponds to lambda equals to 10 log 10. Log 10 of the lambda equals to -1, which is lambda equals to 0.1, right? And then h is going to equal to 0.3. So that's going to be our optimal lambda and h combination, right? And this kind of procedure is actually general enough to be applied to many different problems. The only drawback of this kind of procedure is that it's going to involve much more computational cost. So it's going to take a while for you to actually try out all those different choices for HH and lambda, right? And here we only have like 2 hyperparameters. Suppose if you have like 5, then that's going to be a 5 nested loop, right? And then here you only have like 3 choices for each hyperparameter, so it's 9, right? So it's 3 to the second power, that's 9, right? But suppose you have 3 parameters but you have 5 parameters, and each one try out 3 different values, then it's going to be 3 to the 5th power. Then the number of iterations is going to be huge, right? So it's going to take a while to actually do this calculation or do this cross-validation test, right? But it's actually a quite effective way for you to choose the most appropriate hyperparameters, right? This is more systematic than trying out different combinations of the hyperparameters manually, right? This is automatic. You don't have to sort of do that kind of thing manually, right? And this kind of separating the same set of training data into 2 different groups, one for computing theta hat for training, the other group, the control group, for validation. This kind of idea is actually general. It can be generalized to many different scenarios. And this is our example for cross-validation.